Hi, I'm Aishwarya Konavur, and in this lecture, I want to explain what vision language models are. Welcome to today's lecture on Introduction to Vision Language Models by Togo AI Labs. Today, we will understand what vision language models are, what is the difference between a large language model and a vision language model, different applications of VLMs, and we will also see some famous vision language models. So, let us get started. Large language models or LLMs have a problem. They can process text or a document like a PDF. But do you know how LLMs do this? They do this by using an encoder. By encoding both document and the text prompt we provide as tokens and putting that into LLMs. They process using attention mechanisms and generate a text-based response as an output. It is so good. But let me ask you one question. What if that text document or that PDF, what if it contains an image or a chart or a diagram? Well, standard large language models cannot read images like they process the text. So a picture or a graph or a handwritten note that may contain a valuable information, but that cannot be fully understood by a large language model. And this is where vision language models come into the picture. So what are vision language models? In this video, I'm going to explain what vision language models are and how they are different from LLMs or large language models. And we will also see why we need them. Vision language models are multimodal models that can take text and image files, and then they can generate a text-based output by processing them. So why do we need a vision language model? What kind of tasks that this vision language models can perform? Let me explain this by telling you how a vision language model interprets the text and the image or the visual information. If we have the image of a bird and the text or the word bird, both the image and the text has the same meaning. So how can an AI model understand both this image and text are the same? It represents the same entity. So VLMs connect pixels to words by aligning the representations of both modalities in a common embedding space. So the image and the text, they are converted into vectors and they are represented in a shared representation space or a common embedding space. In this mathematical space, the vector of the image and the vector of the word should lie closer as they have the same meaning. If they should lie closer, then their cosine similarity should be very high, which means the angle between the two vectors in this embedding space should be as minimum as possible. So how can a vision language model work to make this cosine similarity very high or to make the angle between similar entities in the common embedding space low? Let us see. So a vision language model or a VLM understands visual information like images and videos and textual information, language. And why we need VLMs? Well, one of those tasks a VLM can perform is visual question answering. If I show a VLM a picture and I ask it to analyze it, for example, the photo of a cat sitting on a chair near white flowers. For example, if I show this photo to a VLM and if I ask what is happening in this scene, a vision language model can answer this question. VLM doesn't see just the pixels. It recognizes the objects, the people. If there are people, it recognizes the objects, people, and the context. So if I show this picture of a cat sitting on a chair and ask what is happening here, then VLM understand the image, the context, the objects, and the whole scene. And it also has the ability to generate captions for this image. So simply, if I ask what can a VLM do, it can generate captions for images, it can answer questions about an image, and it can document the understanding. it can perform multimodal reasoning. So a vision language model can be used for all of these tasks. Now, say if you have a scanned receipt, the model can organize it and even summarize the receipt for you. So to do this, VLMs doesn't treat the images and text separately. Instead, they merge them. So how do they actually do that? So in if you have the image of a dog chasing a ball, a VLM, if we ask the question, what kind of dog is this? A VLM can answer it. We can use a vision language model to analyze and summarize a receipt or if you have a report, then we can ask the VLM to summarize the report or the receipt. Similarly, if you have a sales report with a lot of chart and figures in it, we can use a VLM to understand the trend and summarize the sales report. So a large language model or an LLM, it can process the text and answer to our questions. But it fails if there is a picture or a handwritten note or a chart in that. But VLMs, it can process the text and it can process the visuals. And they don't process the images and text separately. Instead, they merge them. So let us see how VLMs treat the images and text and how it is processing it. Let us start with the LLMs. LLMs takes the input as a prompt or a text prompt. It is like sending a message to a large language model. The words in that text message or the text prompt, it is converted into tokens, and these tokens, they are the discrete mathematical representations of the language. And these text tokens are then processed through the model's internal representations, primarily the attention mechanism or attention layers, to determine the relationships and contextual meaning. And then it understands the patterns between the words. And finally, we get a text output. That text output can be the answer to our question. So we get the text output as the result of all these text tokenizations and how the LLM processes the text in the document. This is how a large language model works. Now, what VLMs do is VLMs introduce something new into this picture. And that new thing is it introduces a vision encoder. Let us see how a vision language model works. So as we discussed here, an LLM cannot directly work with raw images. It processes text tokens. So if there is an image, it needs to be converted into a format that LLM can understand. And that is where a vision encoder comes into the play. Unlike a large language model which tokenizes the words, the vision encoder processes images as high-dimensional numerical data. And it doesn't see the images in the way humans do. Instead, it extracts things from them. It extracts the patterns, textures, the edges, and the spatial relationships. And after extracting these, it is converted into something called a feature vector or a bunch of feature vectors. Now, these feature vectors, even these feature vectors cannot be directly fed into the LLMs. So now, after getting these feature vectors, now we have a structured representation of the image content. And this feature vector is essentially a dense embedding of the which is the relevant information from the image. And also it discards all the unnecessary details, similar to how an LLM converts text into word embeddings. Now, instead of images, now those images are now converted into vectors. But these feature vectors cannot be directly fed into the LLM. So we need an additional stage here. And this additional stage is the projector. Projector maps continuous image embeddings into tokens, giving us image tokens. And this image tokens aligns with text tokens used by the large language model. Now, at this stage, we have the image tokens and the text tokens. And both are existing in the same latent space. These are now fed into the large language model that process them together using attention mechanisms, analyzing how different tokens relate to one another regardless of whether they originate from the text or they originate from the image. as we discussed first in the same embedding space. And finally, this gives us the text-based response generated by the model, whether that is a caption or an explanation of what is in the image or the answer to a question by interpreting both visual information and the textual information. So to summarize, a vision language model has extended an LLM by introducing a multimodal tokenization pipeline. And this multimodal tokenization pipeline allows images to be represented in the way that text-based transformers can process usually. Now, let us discuss about a very popular vision language model, the CLIP model. So this image is from the CLIP paper published in arXiv with 48,000 citations. This is a 48-page long paper that explains the CLIP model. So instead of explaining the whole long paper, I thought I'll take the image from this paper and figure from this paper and explain how a VLM works for a pre-training and classification task. So here you can see we have the image of a dog here, and we have the caption, Pepper the Aussie pup. There are different images and there are many captions. So these captions are fed into the text encoder and the images are fed into the image encoder. And they are converted into text tokens and image tokens. So this is not an n-dimensional vector. Instead, it corresponds to the first caption corresponds to the token T1. Second caption is representing the token T2. Third one T3. And the nth caption is representing token Tn. Similarly, for the images, the image encoder converts all the images into image vectors or tokens. And I1 is the first image. I2 is the second image. In is the vector for the last nth image. Now, when I explained the common embedding space, I told you the angle between the two vectors in the common embedding space, the angle between the text vector and the angle between the image vector should be as minimum as possible if those vectors are related, and it should be as high as possible if those image and that caption is not related. Ideally, that is the cosine similarity, and it is basically the dot product of these two vectors. It is the dot product of the image vector and the text vector. So if the dot product is the cosine similarity is very high, if we have the dot product as positive, then it means the cosine similarity is very high. And it will be only high if the image and the token are related. If the cosine similarity is very high, it means the image and the caption are related. And it can be considered as a positive cosine similarity or a positive value. And if they are not related, then all these are negatives. So the model has to maximize the dot products or the cosine similarities of the related images and the captions, and it should minimize the cosine similarities or dot products of the unrelated objects in the embedding space. And after computing the dot products, if we have, let us extend the pre-training into something like classification. So if we have different words in a dataset like plane, car, dog, bird, and this step, a photo of object, this is done to make that as a caption instead of a word. So now that caption becomes a photo of a plane or a photo of a dog or a photo of a bird. And a text encoder converts those captions into vectors or tokens, and image encoder, if there is an image that was not present during the training, if that image is also given to the vision language model, the CLIP model, then the image encoder converts this into vector, and ideally it should only match with the image, with the caption of a dog which was there in the training set. If the training set had a caption or the word dog in the caption, then if we give a new image to the CLIP model, it should only relate this visual in the image with the caption related to dog. So to get this, the cosine similarity or the dot product of this image should be only matching with the token of the vector of the dog. So if we compute the dot products, then the image should not match with that of a plane, which is T1, or a car, T2. It should only match with T3, which is a dog. Now the dot product will be maximum for the dot product I1, T3, and the vision language model can give the caption, the photo of a dog for this image. So this image was not present during the training, and this was just contrastive pre-training. And during the pre-training, there were images of dogs and there were captions related to that. It computed the dot products of the captions and images, and it was extended for something like image caption retrieval. So this is not a generation task. Instead, it is a retrieval task. So the images and captions were there. And if we give a new image to the VLM and ask it, okay, what is happening in this picture? It can retrieve the caption from the captions, and it will be related to the dog in the picture. So this paper, you can access the paper. It is the famous clip paper. I'll give the link to the paper in the description box. You can directly access it. And now let us come to the challenges of VLMs. So all these sound great, but VLMs are not without their challenges. For example, if we consider the tokenization bottlenecks, text tokenization is efficient because models break down words into subtokens, but images lack a natural token structure. They must be first encoded, and then the encoded image requires a lot of tokens. So this increasing memory usage, it can slow down the imprints. And some models do incorporate optimization strategies like the receiver sampler. But the fact remains that processing images remains more computationally intensive than processing the text alone. Now, similar to traditional large language models, vision language models can also produce hallucinations, generating responses that sound plausible but are factually incorrect. This happens because VLMs don't really see the images as humans do. They are learning statistical associations about them, which can lead to assumptions about objects in an image. For example, if we have a vision language model trained predominantly on the internet scale datasets, it may misinterpret the images. So, coming to vision language safety, as we said, a vision language model aligns images and text representations in a shared space. So if we have the image of a pedestrian and the word pedestrian, ideally in this shared representation space, they should lie closer. So sometimes inherent bias in the vision language models can distort this alignment, leading to dangerous misinterpretations and safety risks. So one safety risk is if a human is driving a car and if it is dark and a pedestrian wearing a dark clothing crosses the road. When a human is driving the car, human can take action if they see the pedestrian wearing the black clothing, and they can stop the vehicle. If that is a self-driving car and they are using AI models to take actions like a vision language action model, then this misalignment, sometimes the dark clothing can be mistaken for the background. So this misalignment can lead to dangerous life hazards. So if the pedestrian is wearing a black clothing and that black clothing is misinterpreted as the background, then the model fails to detect that pedestrian and it failed to take the action for stopping the vehicle. So this makes the research in this vision language model very, very important. And I should say one of our recent papers in vision language model, quantifying the bias in vision language models. It got accepted in 2 ICCV conferences this year, and our work was on quantifying the gender bias in vision language models. And it was very surprising that the transformer-based vision language models and convolution-based vision language models, they were displaying a great gender bias, and we were able to quantify that. So this makes the research in this vision language models very important, as we are using more large language models and vision language models on a daily basis. And vision language models are learning from internet data. And this makes the research in this direction very, very important. So in Togo AI Labs, we have a 4-month research program on vision language models, where you can work with me on high quality vision language model research projects, which we will target to publish in reputed journals and conferences. So if you are interested in working with me on vision language model research project, do check our website, togolabs.ai, and explore our courses. Feel free to enroll in our courses and let us work on something amazing together. So I hope this video, this lecture gave you a clear idea on how a vision language model is different from a large language model. Where can we use a vision language model, how a vision language model work, and its applications. So if you like the video, stay tuned for more videos related to vision language models and other AI topics. So thanks for watching. See you soon.